Hi and welcome to the last installment on the video series on systems of linear equations. The first one we looked at putting equations into matrices in matrix form. The second video we looked at solving simultaneous equations using matrices. The third one we looked at the three different types of possibilities that can happen with linear graphs and how to solve those using matrices, but also I guess using the old year 10, year 11 sort of rearranging method. The last one is, I guess, the application of the previous video, and to be honest, this is where the exam questions are at. So this is the one that you probably need to understand more than any of the other ones, even though if you understand all the other ones, you'll probably understand this one as well. So this one here is, this video will be looking at three questions from the exams, exam 2007, 2008 and 2009, I believe, and questions that are not very well done by students. This one was 36% of people got it correct. The next one, I believe it was only 45% people got it correct. And then finally only 49%. So I think they have got better in the last couple of years. People have started to understand them a little bit better, but still they're not very well done. And I know that each year our classes sort of struggle with this. So hopefully you guys can learn it really well and master it. So this question here says that this equation here and this equation here has only one unique solution when m is some of these numbers here, and we have to get, we have to work out which value of m will give this only one unique solution. So again, the theory of it, one unique solution means that they cross over at some point, which means that their gradients are not the same, and that's the key to this whole thing. m1 is not equal to m2. So when I rearrange this equation, y 12y equals negative mx plus 24, and I get y equals negative 12 on m on 12. Make it a little bit neater. Negative m on 12x plus 2, and so that's the first one. And then I rearrange the second one, and I get my equals negative 3x plus m, and I get y equals negative 3 on mx plus m on m, which is actually just m on just 1. Now what we're saying is that the gradients are not the same. It's very difficult to work out when the gradients are not the same. It's much easier to work out when they are the same and then say everything except for those numbers. So for example, and I guess I'm going to do this question, one, doing it the rearranging method, but then I think the far quicker way is to do it using matrices. But I think this kind of helps you understand what's going on, whereas sometimes I feel like matrices is a bit abstract. I'm just kind of applying something and I'm getting an answer. But matrices is much quicker and much more efficient than what we're doing here. But anyway, I'll push on with this one. So I've got these two graphs here, and I'm working out when the gradients are not the same. Now, as I mentioned, it's much easier to work out when they are the same, so I'm going to do that. M over 12 equals negative 3 over m. Okay, I can divide both sides by negative and get rid of that. Multiply both sides by m, so I get m squared. Multiply both sides by 12, and I get 36. So m squared equals 36. So if m will equal plus or minus 6. Now, if m equals plus or minus 6, then the gradients are the same. If m doesn't equal positive or negative 6, then the gradients are not the same, which means that they will cross over at some point. They will have a unique solution. So the answer to this one, don't be fooled by A. A is the dummy answer, to because that's when they are the same. What we want it when they're not the same. So we actually want the answer of C. This here, I hope you've seen this before, but if you haven't, that means all real numbers except for the numbers negative 6 and 6. So those curly means the set of, so negative 6 and 6. So R means all real numbers, all numbers that exist, unless you're doing a silly subject like specialist, and they can find other answers that don't exist. All real numbers except for negative 6 and 6. So the answer in this case would be C. I want to show you how to use matrices on this one as well, because I feel like it is much quicker once you know how to do that. So for matrices, I need to remember that if I want to get that the gradients are not the same, I need the determinant. Sorry, the other way around. If I want to find out when the gradients are the same, I need the determinant to be equal to 0. So I'm going to find the determinant. I get m12 3m, and I'm going to say that m squared minus 3 times 12, which is 36, so that times that minus that times that, is equal to 0. If that happens, if it's equal to 0, then we have the gradients the same. Okay, that will mean m1 equals m2. So as you can see from here, m squared equals 36, so m equals plus minus 6. That means that the gradients are the same, and again, I'm back to where I was before. I want it when they're not the same, so therefore C would be the answer. I feel like using matrices is much quicker than using the rearranging method, but as you can see, it's a little bit abstract. We don't kind of know what we're doing over here. We're just using formulas and punching out numbers, but it's much quicker to do it this way. So it doesn't matter which way you do it, but you do need to know both of them. So we'll have a look at the next question. For the next question, I'm only going to do it using matrices because I really want to push you in that direction. But if you want to do it the other way, then that's okay as well. So again, I look at this. There's two lines. They're both linear lines where a is a real constant. Find where a is a real constant and they have an infinitely many solutions. So we need to remember what that means. That's m1 equals m2 and c1 equals c2. They're actually the exact same graph. So I'm going to find out when m1 equals m2. I'm going to use matrices, and I'm going to get this a3, 2, and a plus 1. Now I'm going to get the determinant, which is a times a plus 1 minus 3 times 2, which is 6, and I'm going to force that to equal 0 because that will be when my gradients are the same. And I get a squared plus a minus 6 equals 0. I use the cross method or whatever other method you want to do, and I get a plus 3, a minus 2. Okay, and so now I can find out that a equals negative 3 and positive 2. Now at this point I don't know really what that means. I know that if a is negative 3 or 2 that they will have the same gradient, but I don't know whether they are in fact parallel or whether they are the exact same graph. All I know is that the gradients are the same. So now I need to sub these numbers back into the original equations to find out whether they are parallel or whether they are in fact the same graph. So there's no real quick way to do this, unfortunately. A is negative. Actually, you can do this all on your calculator very quickly and easily, but I want to have a look at it by hand because it could come up in a non-calculator question. So I'm going to sub negative 3 into A is negative 3 into both of those equations and see what I get. So I get negative 3x plus 3y equals 0, I believe. I'll just make sure. Yes. And 2x plus 2y equals 0. And hopefully we minus 2y. I knew that there was a mistake somewhere. Okay, so as you can see that these two graphs are exactly the same. If you rearrange both of those, you're going to get a y equals x for both of them. Okay, so if a equals negative 3, then these graphs are in fact exactly the same. So this one is infinite. But I'm not sure about the other one. I do need to test the other one. So if a equals 2, I'm going to sub that in as well. So I'll get 2x plus 3y equals 0, and I'll get 2x plus, I believe it's 4y equals 0. Just make sure of that. If x is 2, 2x plus 3y, yeah. And, oh no, that will be 2 plus 1, which is 3. So let's have a look. Actually, these are identical graphs as well. So it doesn't matter whether a is negative 3 or 2, both of them will give you an infinite number of solutions. If a is not negative 3 or 2, then we have a situation where we have one unique solution. They cross each other once, but in this case they're both an infinite number of solutions. So our answer will be, having a look through, it's not real numbers, it's not anything but that. That would be for one unique solution. It's going to be this one here, negative 3 and 2. Okay? Right. The next one we're going to have a look at is sort of similar, but this one says, we're back to one unique solution again. So again, I'm going to use matrices because I believe it's the quickest way of doing things. Remember, one unique solution means that the gradients are not the same. Now what I need to do is I need to use the determinant to find out when the gradients are the same, and then say anything but those two things. So the determinant, k negative 3 to 3, 5 and negative k plus 2. I feel like some people will make a mistake with that one, hopefully not. So now I make that negative k multiplied by k plus 2 minus negative 15, which is positive 15. I'm going to force that to equal 0. And I'm just going to drag that onto the other side so it's positive, or divide everything by negative 1 if you want to do that. Just because I like dealing with the squared term to be positive rather than negative. So I'm going to get this here. So that's k squared plus 2k minus 15 equals 0. And then I use the cross method or whatever other method you want to use, and I get k plus 5, k minus 3. Hopefully I haven't made a mistake on that. So k equals negative 5 and positive 3. Now again, if k is negative 5 and positive 3, that means that the gradients are the same. We've either got a unique, an infinite number of solutions, they're the same graph, or we've got two graphs that are parallel. But we need to actually answer our question. Our question says, when does it have a unique solution? That means anything except for when k is negative 5 and 3. So our answer, again, up the top, number A is, is the dummy answer. I think the B looks about right, negative 5 and 3. So hopefully you've understand how to do these types of questions. There's plenty of them around. Just ask me for a few more if you would like to try a few more of these. You need to be able to do them, probably both methods, rearranging it and finding it out. But I think, to be honest, after you've done that a couple of times, then move on to the matrices, because I just feel like they're so much quicker and so much easier to do, far less work involved, and you get the same sort of answer. So thanks for watching the series on matrices. If you have any questions about any of it, please feel free to watch it again, or come and ask me some questions about it. Thanks very much.